When dealing with a 600 amp service and multiple 200 amp service panels, understanding the grounding electrode conductor or GEC and equipment grounding conductor or EC requirements is crucial for safety and code compliance. According to the National Electrical Code, specifically Table 250.66, a 600 amp service with service entrance conductors consisting of two parallel 500 mcm aluminum conductors necessitates a 2/0 AWG copper grounding electrode conductor. The question often arises whether this GEC can be run continuously through lay-in lugs in each of the service panels or if separate conductors are required for each panel. The NEC permits running the GEC in a continuous fashion through lay-in lugs, provided these lugs are properly rated for the size and number of conductors used. This method simplifies the grounding system while ensuring effective grounding. The next important aspect is the equipment grounding conductor. For the EGC from a bonding bushing at each raceway to the ground bus, a number 4 AWG copper conductor is sufficient. This conductor serves to bond metallic components of the electrical system, providing a low impedance path for fault current. Now, let's delve into the specifics of bonding the 4 service panels to the GEC. This is a critical step in ensuring that all panels are at the same ground potential. Connect all 4 service panels to the GEC using bonding jumpers. A recommended method involves connecting a number 4 AWG copper bonding jumper from the CT-CIN to the ground bus in each panel. Then connect the lay-in lug on the GEC to the bonding jumper in each panel. This creates a robust and reliable grounding system. To summarize the process, firstly, determine the appropriate size of the GEC based on Table 250.66 of the NEC, which, in this case, is a 2/0 AWG copper conductor for 600 amp service with 500 mcm aluminum service entrance conductors. Secondly, run the GEC from the CT-CIN through lay-in lugs in each of the 4 200 amp service panels, ensuring the lay-in lugs are rated for the conductor size and number of conductors. Thirdly, connect a number 4 AWG copper bonding jumper from the CT-CIN to the ground bus in each panel. Fourthly, connect the lay-in lug on the GEC to the bonding jumper in each panel. Fifthly, ensure that all metallic raceways entering the service panels are properly bonded using a number 4 AWG copper equipment grounding conductor from a bonding bushing to the ground bus. Sixthly, verify that all connections are made according to manufacturer's instructions and local electrical codes. It's also important to consider the different types of grounding electrodes that can be used in conjunction with the GEC. These include ground rods, water pipes, and other approved grounding electrodes as defined by the NEC. The specific type of grounding electrode will depend on site conditions and local requirements. In addition to the grounding electrode conductor, the equipment grounding conductor plays a vital role in ensuring electrical safety. The EGC provides a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices such as circuit breakers and fuses. Proper sizing and installation of the EGC are essential for minimizing the risk of electrical shock and fire. The NEC provides detailed requirements for EGC sizing in Table 250.122, which takes into account the size of the overcurrent protective device protecting the circuit. Furthermore, the NEC specifies acceptable methods for installing the EGC, including running it within the same raceway as the circuit conductors or using it as part of a cable assembly. When installing bonding bushings, it's important to ensure that they are properly tightened and make good electrical contact with the metallic raceway. This helps to create a continuous low impedance path for fault current. Additionally, bonding jumpers should be securely connected to both the bonding bushing and the ground bus in the service panel. These connections should be made using listed connectors and installed according to manufacturer's instructions. It's also crucial to consider the impact of voltage drop on the performance of the grounding system. Excessive voltage drop can reduce the effectiveness of the grounding system, making it more difficult for overcurrent protective devices to operate quickly and reliably. To minimize voltage drop, it's important to use appropriately sized conductors and minimize the length of the grounding conductors. In cases where long runs of grounding conductors are necessary, it may be necessary to increase the conductor size to compensate for voltage drop. Another important consideration is the type of grounding electrode used. The NEC recognizes several types of grounding electrodes, including ground rods, ground plates, metal underground water pipes, and concrete encased electrodes. Each type of grounding electrode has its own advantages and disadvantages, and the selection of the appropriate type will depend on site conditions and local requirements. Ground rods are a common choice for grounding electrodes, particularly in residential applications. They are relatively easy to install and can provide a reliable ground connection in most soil conditions. However, ground rods may not be effective in areas with high soil resistivity. Metal underground water pipes can also be used as grounding electrodes, provided they meet certain requirements. The water pipe must be in direct contact with the earth for at least 10 feet, and it must be electrically continuous. Concrete encased electrodes, also known as U for grounds, are another option for grounding electrodes. They consist of a length of bare copper conductor encased in concrete, typically in the foundation of a building. Concrete encased electrodes can provide a very low impedance ground connection, particularly in areas with poor soil conditions. Regardless of the type of grounding electrode used, it's important to ensure that it is properly installed and maintained. Grounding electrodes should be protected from physical damage and corrosion, and they should be periodically inspected to ensure that they are still providing a reliable ground connection. In addition to the requirements for grounding electrode conductors and equipment grounding conductors, the NEC also includes requirements for bonding of metal enclosures and equipment. Bonding is the process of connecting metal parts of an electrical system together to create a continuous electrical path. This helps to ensure that all metal parts are at the same electrical potential, reducing the risk of electrical shock. The NEC requires that all metal enclosures and equipment be bonded together, including service panels, raceways, and equipment frames. Bonding can be accomplished using a variety of methods, including bonding jumpers, bonding bushings, and grounding lock nuts. When installing bonding jumpers, it's important to ensure that they are properly sized and securely connected. Bonding jumpers should be made of copper or other conductive material, and they should be sized according to the requirements of the NEC. Bonding bushings are used to bond metal raceways to enclosures. They are installed on the end of the raceway and provide a connection point for a bonding jumper. Grounding locknuts are similar to bonding bushings, but they are used to bond metal boxes to enclosures. They are installed on the end of the box and provide a connection point for a bonding jumper. In addition to the requirements for bonding, the NEC also includes requirements for overcurrent protection. Overcurrent protection is the process of protecting electrical circuits from excessive current flow. This is typically accomplished using circuit breakers or fuses. Circuit breakers and fuses are designed to interrupt the flow of current when it exceeds a certain level. This helps to prevent damage to electrical equipment and reduce the risk of electrical shock and fire. The NEC requires that all electrical circuits be protected by overcurrent protective devices. The size of the overcurrent protective device must be appropriate for the size of the circuit conductors and the load that the circuit is serving. Circuit breakers and fuses must be installed in readily accessible locations and must be properly labeled. In addition to the requirements for overcurrent protection, the NEC also includes requirements for ground fault protection. Ground fault protection is the process of protecting electrical circuits from ground faults. A ground fault occurs when current flows from a live conductor to ground. This can happen if a wire comes loose and touches a metal enclosure, or if insulation on a wire breaks down. Ground faults can be dangerous because they can cause electrical shock and fire. The NEC requires that ground fault protection be provided for certain types of electrical circuits, including those that serve bathrooms, kitchens, and outdoor areas. Ground fault protection is typically provided by ground fault circuit interrupters, or GFCIs. GFCIs are devices that monitor the flow of current in a circuit and trip if they detect a ground fault. GFCIs are very effective at preventing electrical shock and fire, and they are required by the NEC in many locations. The grounding system plays a critical role in electrical safety by providing a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices and minimizing the risk of electrical shock. A properly designed and installed grounding system is essential for ensuring the safety and reliability of electrical installations. It's important to consult the NEC and local electrical codes to ensure compliance with all applicable requirements. Additionally, it's recommended to engage a qualified electrician to perform grounding system design and installation to ensure that the work is done safely and correctly. In summary, when dealing with a 600 amp service feeding multiple 200 amp panels, the grounding electrode conductor should be sized according to NEC Table 250.66, which dictates a 2/0 AWG copper conductor for the scenario with 500 mcm aluminum service entrance conductors. The GEC can be run continuously through lay-in lugs in each panel, provided the lugs are rated appropriately. A number 4 AWG copper conductor is sufficient for the equipment grounding conductor from bonding bushings at each raceway to the ground bus. Remember to bond all 4 service panels to the GEC using number 4 AWG copper bonding jumpers from the CT-can to the ground bus in each panel, connecting the lay-in lug on the GEC to the bonding jumper. Always adhere to local codes and manufacturer's instructions for proper installation. These steps, when meticulously followed, ensure a safe and code-compliant electrical service.